All right, let's take a look at square root function. So a function defined as square root of x, where of course x would have to be greater or equal 0 in order for square root of the number to be a real number, is called the square root function. What about graphing? Pause the video here, plug some points in like x equals 0, 1, 4, and so on. See what the graph would look like. Go ahead, try it on your own. Assuming you've come back, so 0, square root of 0 is 0, square root of 1 is 1, square root of 4 is 2, square root of 9 is 3. So that would be the graph of the square root function. So domain would be 0 to infinity, and range would also be 0 to infinity. You can see that from the graph, right? Is it a one-to-one function? Yes. You can see it passes horizontal line test. Well, if it's one-to-one, we should be able to find its inverse function. Let's take a look at what would be g of 2/3. So you replace, again, look, g of blank would be square root of the blank, whatever goes in. So if 2/3 goes in, we have to take square root of 2/3. If you wanted g of 100, then you would have to take square root of 100, which would be 10. G of 3,456 would be square root 3,456. Inverse function. So y equals square root x, and again interchange x and y, solve for y, and you'll get g inverse is x squared, and the restriction would be x greater equals 0. It's not the entire x squared function, just a part of it. And so if you look at the graph, so the blue graph, that was our original square root function. And again, if you reflect it across the y equals x line, you will get y equals x squared. But it's not the entire parabola, just the parabola for x0 and higher. So polynomial functions. Polynomial functions are written as p of x equals, and then a generic polynomial, constant term a sub 0 plus a sub 1x plus a sub 2x squared, and so on, up to a sub n x to power n. So as powers of x's multiplied by some real number coefficients. Coefficient of the x squared term is called a subscript 2. The subscripts allow us to say that's the coefficient of degree 2 term. The degree of the polynomial, as you recall, is the highest power of x that appears there, which in this case would be n. So again, you can see, because it's a polynomial function, we can put any x we want. And so that would mean that we get all real numbers as our domain. And then the range is also all real numbers if n is odd. But if n is even, then it's a little more difficult to determine what the range is. We will have to look at that a little bit later. So let's take a look at the constant function, which is a special case of polynomial function, which is a polynomial degree 0. So constant function is where the output is always a real number, the same real number. So no matter what x is, the output is always a. So how would you graph something like that? Well, y equals a is a horizontal line, right? So depending on what the a is will determine where the y equals a line is. So again, domain would be all real numbers. In this case, the range is a singleton point a. It is one-to-one or not? The answer is no, because it is a horizontal line, so infinitely many inputs provide the same output. So it is not a one-to-one function, so it does not have an inverse. So what does that mean? If I have f of x equals 5, then what does that mean? It means that when I plug in 2/3, output is 5. So f of 2/3 is 5, f of 100 is 5, f of negative 3,456 is 5. What about f of a plus h? Is also 5. No matter what the input, output is always 5. So here's the graph of y equals 5, a horizontal line passing through 0, 5. A linear function, that's a degree 1 polynomial, which you already know is a straight line. So you can write it as f of x equals mx plus b, m non-zero, to make it degree 1 polynomial. M is the slope of that line, and b is the y-intercept. Some of you may have seen that in your previous classes. So this is a degree 1 polynomial, and it's written in slope-intercept form of a line. Domain and range are both negative infinity to infinity. And again, because the m is non-zero, we have a one-to-one function. And you can try plotting the following example. F of x equals 2x minus 3. Plot the graph and then find f of -1, f of 0, and f of 4. Go ahead and do that on your own. Pause the video here and let's see what you got. See if you can also sketch the graph of that function, and also, if you're able, find its inverse function. Go ahead, pause the video. Don't just wait for me to do it. All right, let's see what we got. F of -1, plug in -1 for x. So -1 times 2, which is -2 minus 3, which will give us -5. F of 0, 2 times 0, 0, minus 3 is -3. F of 4, 2 times 4 minus 3, or 5. All right, so inverse function, remember, right, y equals 2x minus 3, interchange x and y, and solve for y. So there's our inverse function, x plus 3 over 2. And now the graph of it. So again, because f and f inverse are simply lines, you just have to plot the y-intercept and the slope. So y-intercept for both f and f inverse are -3 and 3/2 respectively, and the slopes are 2 and 1/2 respectively. So here we go. You know how to graph them, and you can see again 2 is the slope. So here are the two. The blue is the original function, and the red is the inverse function. So 2x minus 3, and then x plus 3 over 2. Square function is another polynomial function of degree 2 and is called a parabola. And again, to plot this graph, go ahead and make a chart. Plot x equals -2, -1, 0, 1, and 2. See what kind of graph you get. Go ahead and do that. Pause the video here, please. All right. So we have, this is the graph you probably got, -2, 4, -1, 1, 0, 0, 1, 1, and 2, 4, where you plot, when you plot points, that's what you'll get. Domain is all real numbers, but the range is 0 to infinity. 0 is included because when you square, you always get positive values. Is it a one-to-one function? Nope, not a one-to-one function. Does not pass horizontal line test. You can see that from the graph. All right, let's see if you can then find the inverse function if you restrict the domain, because otherwise it does not have an inverse function. What would you have to make the domain if you wanted to find inverse of this function? 0 to infinity or -infinity to 0. Then you could have an inverse. All right, let's see what you have then. F of 2/3 is 2/3 squared or 4/9. F of -2 would be -2 squared or 4. F of 2 would be 2 squared or 4. F of a plus h. So instead of x, you're putting a plus h, which will give you a plus h squared. This brings up another quantity that we may want to consider, especially if you're going on to business or STEM major or some other class where this is a prerequisite. A lot of times, practical applications require you to find difference quotient. So remember, when you take a plus h bracket squared and you square it, you'll get a squared plus 2ah plus h squared. So if you were asked to find f of 2 plus h minus f of 2 over h, the first question is, what is this and what does it mean? So in order to do that, let's just compute it algebraically first, and then we'll look at what it means. F of 2 plus h, so you're going to put 2 plus h in place of x. So you will end up with 2 plus h squared minus 2 squared, because that's what f of 2 is, and then divided by h. Again, you can see the h comes from 2 plus h minus 2. So it looks like y-coordinate difference over x-coordinate difference, or slope of a line. And we'll see what that is in just a little bit. And then perform the algebra. 2 plus h squared, open the brackets, will be 4 plus 2h plus h squared, minus 2 squared, which is the 4, subtract, reduce, pull the h from the numerator out, which cancels out with the h from the denominator, divide it out, and you're left with 2 plus h. The question is, what does this mean? So let's look at it a little more thoroughly in a graphical form to see what all these quantities mean. We're going to use a graphing utility to see what is going on. So here's the graph of y equals x squared. Let's plot the point 2, 4, which is right there. Let's plot the point 2 plus h squared, which is our function at x equals 2 plus h. So the y-coordinate would be 2 plus h bracket squared, like you see. And now let's control the h and see what happens to this line that goes through b and a. So if you look, let's move. You can see that as h goes to 0, that the point b moves closer to this point a. So let's take a look at the slope. 2 plus h squared minus 2 squared over 2 plus h minus 2. That's the slope or difference quotient that we are computing, which gives you the slope of this line right there. Difference of y coordinates divided by difference of x coordinates. So you can see how the slope changes as you get closer to a. And it looks like as you get closer and closer, you can see that this b to a, this line, is almost a line that's called the tangent line, which is this red line that I've graphed. If you zoom, you will see that the line can get closer and closer to the tangent line, which is a line going through a when h is 0. So again, you can see that this line here, let's zoom back out so you can see what's going on. The black line actually gets closer and closer to the red line, which is the tangent line, as h gets closer and closer to 0. This line going through BA is called the secant line, and the red line is called the tangent line, which gives you how fast the graph is changing, or increasing or decreasing. So if you're interested in that, you'll have to take the next class, which is basically calculus. All right, let's take a look at the next function. Next polynomial function we'll focus on is f of x equals x cubed, or called cubic function. Again, to graph it, plot coordinates x equals -2, -1, 1, and 2. Cube it, see what happens, and then we'll check. So pause the video here and let's see what you got. So you should have gotten domain to be all real numbers, range to be -infinity to infinity. You should have had that it's 1 to 1. If you plug in some coordinates, you will see what the values are. And so inverse function, you just undo the cube, it will give you cube root. And then here's the graph of the functions 0, 0, 1, 1, 2, 8, -1, -1, -2, -8. If you want to plot its inverse function, just interchange x and y coordinates, and you should see this red graph would be the graph of the inverse function. So that's just a quick summary. We will spend more time with these graphs a little later. Let's look at the extension questions you can ask now. If you know how the x squared graph looks like and x to the third graph looks like, one of the questions you might want to ask yourself is, if you know x squared graph, what would be the graph of x to the 4? What's the difference between the two? And once you figure that out, you may want to explore what is the graph of x to an even power. When you know how the graph of x to the third looks like, what would be the graph of x to the fifth? How are they different from each other? And then in general, can you expand it to observations to x to any odd power? So this we would like you to explore on your own. Let's take a look at a few more extension questions. In polynomial functions like f of x equals x squared, the variable is the base and the exponent is fixed. So since you're a mathematician, you would want to know, well, what happens if you reverse that? What if the exponent, which is the 2, becomes the base and the base becomes the exponent? Well, then it would look like f of x equals 2 to the power x. Is that even a function? And if so, what happens in general if you have f of x equals a to the power x? What kind of questions would we want to ask then? We want to know what kind of numbers would be valid as a to make it a function. So what numbers would work for our base? Would this function be 1 to 1? And then if it is 1 to 1, what would the inverse look like? Those are the questions. So pause the video here, explore these functions, and then continue the video. So you can see that 2 to the power, a positive power or a negative power, you've seen in a previous classes that yes, that would be valid. For example, fractional powers would make it radical, negative exponents would make it fractions, and so on. But can we have a to be any base? So if a was say negative 2, negative 2 to the half power, negative 2 to the half power would be square root of negative 2, which would not be valid. So right away, it would be a complex number, imaginary number, not a real number. So right away, we know that a cannot be a negative number. The base cannot be negative. But the base could be 0. Well, that causes its own problem. 0 to any power would be 0, but 0 to the power 0 is undefined, right? So what about a equals 1? Well, 1 to any power would be 1. So that's not very exciting. So any power between a, the base a can be any number between 0 and 1 or bigger than 1. That's when some interesting things happen. If you graph a few, you will see that it actually turns out to be a one-to-one function, which means that it does have an inverse. So let's go see what that looks like. So exponential function in general is written as f of x equals a to power x, where a is not equal to 1, and it's a positive real number. And if you plot a few points when a is bigger than 1, like 1, 0, 1, when a is 2, 2 to the power 1 is 2, 3 to the power 1 is 3, and so on. So that is this graph here. And as x coordinates become smaller and smaller, you have fractional powers. And you know you can never have a negative number because a positive number to an exponent is going to give you positive numbers. But the fractions, if the bottom gets bigger and bigger, will go to 0. So these values go very quickly to 0, and these values shoot to infinity. If a is smaller than 1, though, the reverse happens. A positive exponent and a fraction power, the higher the exponent, the smaller the number. A negative exponent will give you a reciprocal of the number, so that's why you're getting bigger numbers when you have negative exponent. The line that you see here, that's dotted line, is called an asymptote. An asymptote is a line to which the function gets closer and closer to either when x goes to infinity, that means x gets larger and larger, or x goes to negative infinity, gets smaller and smaller. So we'll look more detailed about the asymptotes later, but the basic shape for exponential functions when bigger than 0 is this red graph, smaller than 1, and bigger than 0 will be this graph. The domain, then you can see, is all real numbers for both of them, and the range is 0 to infinity. 0 is not included because any positive number raised to an exponent will never give you 0. So that's our exponential functions. Let's do some And yes, it is a one-to-one function. You can see it passes horizontal line test. So pause the video here and see if you can actually evaluate the functions at these values. Go ahead. So you have f of -1, f of 3, f of -3, and f of a plus h. Assuming you've come back, we have 2 to the power -1, which will give you 1/2, 3 to the power. So 2 to the third power will give you 8, 2 to the -3rd power will give you 1/8, 2 to the power a plus h would be the last one. So hopefully you got those. So go ahead and now find the inverse of this function because it's a one-to-one function. Go ahead and see what you can do. Pause the video here and see what you can do. So here we go, y equals to the x, interchange x and y to get the inverse, but now we have no way to solve for that y. We need to get that y down, and we can't do that. So we develop a new notation here. We say that y is going to be log base 2 of x, and that's how we write our inverse function. So if our inverse function for 2 to power x has to be written with a new notation because there is no way to solve the equation. You read that as logarithm base 2 of x, or log base 2 of x. Well, what does that mean? Well, the domain of the original function is -infinity to infinity, and so that will be the range of the inverse function. We know the range of 2 to the x is 0 to infinity, so that will be the domain of this inverse function. So we do know what the domain and range of the function is. But let's take an example of what it means to evaluate it. So if you wanted to evaluate the inverse function of 2 to the x, so log base 2 of 8. Well, what does that mean? It means that you are looking for what exponent of 2 gives you 8. You're looking for an exponent. So always remember that the value of log base 2 of 8 is an exponent. What exponent? The 1, 2 to the power, that exponent, 2 to the power 3 gives you 8. So the graph of 2 to the power x is this. What do you think is the graph of the inverse function? Pause the video here and see if you can sketch the graph of the inverse function. Remember, if you plotted a few points, all you have to do is interchange x and y coordinates and see what happens. All right, so here we go. Log base 2, then 0, 1 will become 1, 0. Coordinate 1, 2 will become 2, 1. Coordinate when x is 2, you have 4 will become 4, 2, and so on. So logarithmic functions are inverse functions of exponential functions. And so that means that the a cannot be 1, and it will have to be a positive real number. And all it means is that it's the value of the exponent. A to that exponent gives you x. That's all it means. So generic graphs, if a is bigger than 1, will give you this graph. If a is smaller than 1, will give you this graph. And so domain is 0 to infinity. Range is all real numbers. And again, y is here, x is here. So x equals 0 is a vertical asymptote because it's a vertical line to which the graph gets closer and closer to. We will spend an entire section on log and exponential functions, but we just want to introduce them to you here. And yes, it is a one-to-one function, of course, because it is the inverse function of a to power x. So evaluating log base a of x means finding the exponent that gives you x. So if f of x is log base 3 of x, then what do you think would be f of 1 over 9? Pause the video and see what you can do. Good. You know 3 squared is 9, so it would be -2. And what about 3 then? 3 to what power is 3? 1. Very good. So 3 to the power negative 2 is 1/9, and 3 to the power 1 is 3. So natural logarithm and logarithm base 10 are a few log functions you need to know. Let's talk about when base is 10. When base is 10, instead of writing log base 10 of x, we just write log x. If you look on your calculator, you will see a log key, and that's what that is. It's base 10. Because it's very widely used, the base is not written. It's simply assumed that it's base 10. So in other words, if I wanted to evaluate log of 1,000, remember, it's base 10, so you're looking for 10 to what power gives you 1,000? So that would be what? 3. 0.01, log of 0.01. 10 to the power of negative 2 will give you 0.01. 10 to the power 0 will give you 1. We will spend more time on these later. Also, if you look at the number 1 plus 1 over n to power n as n goes to infinity, it keeps on getting bigger, but once it gets closer, 2.718 dot dot dot, that's actually an approximation of the number called e, which is used to represent natural logarithm. It is also a number that appears in nature often, and so another logarithm function that we'll be working with is called natural logarithm, which is the inverse function of e to the power x. So natural log of e squared would be what? You're looking for e to what power gives me e squared? That would be 2. Natural log of 1 over e to the third will be negative third, because e to the negative third is 1 over e to the third. And natural log of 1 would be 0. In fact, log of 1 base anything is going to be 0, because that is the only power that makes base to 0 power 1. All right, this next function is called piecewise function. Graphical interpretation is easy. You can see it's a function that's broken into pieces. It's not one continuous piece. Such functions are called piecewise functions. Well, how would we define that? So let's just talk about that. Piecewise function is defined exactly how we just said. It's defined in pieces. So domain is broken into chunks. So this function, we can say between negative 2 and negative 1 is taking the value of negative 1. Between negative 1 and 0 takes on the value 0. Between 0 and 1 takes on the value of 1. And you can see the left-hand point is included, right-hand point is not included. So this is what this function is, piecewise function. Let's take a look at what it actually means. If I said, what is f of 0.5, where you would locate where is 0.5 on the x-axis, which is here, and f of 0.5 would be 1 then. So depending on which piece it belongs to will change what output you're going to get. So you have to look at your domain, see where it belongs, to figure out what output belongs to it. So domain is negative 2 to 1 in this case, and the range is singleton points, negative 1, 0, and 1. So if I ask you to evaluate f of negative 0.5, pause the video here and see what the output would be. Good, negative 0.5 is here, which means that the output would be 0. F of 0.5 would be 1. F of negative 1.5 would be negative 1. And that's because of where they fit. We'll spend a little more time on these functions. So let's look at the next example. So see if you can figure out what this next example would look like. Sketch the graph of it, and then we'll work on it a little more. Go ahead, pause the video here and see what you can do. Let's start with negative x plus 1. 1 is the y-intercept. Slope is negative 1 down 1 over 1. But we only want this graph negative 5 to negative 1. So x equals negative 5, that point here. X equals negative 1, that point there. That's the only piece of that line we want. So the rest of the line we erase. All right, next piece, it's x squared But again, we only want the piece between -1 and 1. So we'll have to plot that first and then erase the rest of it. So here's -1 to 1 for x squared, and we have to erase the remaining red graph because that's not what we want. We don't want the whole thing. All right, pause the video here, see if you can do the last piece. 2 to the power x is that graph, and again, we do not want the whole graph, just 1 and up. So x equals 1 will be right there, and then up, and then the remaining graph we have to erase. So this is our full piecewise function f of x that is given here. All right, let's look at one last function in this video, and that's the rational function, which is numerator over denominator. This function only makes sense if the denominator is non-zero. So in the domain of this function, the denominator function always has to be non-zero. So the domain is all x values that would make sense in numerator and the denominator. Both numerator and denominator are polynomial functions. And always make sure that this is in the reduced form. So p and q cannot have any common factors. So simple rational function would be 1 over x. Let's see how we can make sense of this function. Could you graph it? Plot x values and put the coordinates on the graph paper and see how the function would look. If you have trouble, let's just take a look at domain and range. Denominator cannot be 0, so domain would be -infinity to 0, 0 to infinity. And we have 1 divided by something, which means that you're always going to get non-zero real numbers. So the range would also be -infinity to 0. All right, let's take a look at the graph. So plug in coordinates. X equals really small values, positive and negative, and then really large, positive, and then -10, -100, -1000, and see what happens. Pause the video, see what the graph looks like then. And so you can see when you plug in -0.1, 1 over -0.1 is -10, 1 over -0.01 is -100, and so on. If you plug -10, you get -0.1, -100 will give you -0.01. So as x gets closer to 0 from the positive or negative side, these values are becoming very large positive, so shooting to infinity. In the negative side, shooting to -infinity. When you actually let x become infinity, the values become really small or closer and closer to 0. On the positive side, when x goes to -infinity, the values are still close to 0, but on the negative side. So if you plot these coordinates, this is the kind of graph you will see. And this, again, horizontal line, the red horizontal line, graph gets closer and closer to, so will be y equals 0 is horizontal asymptote. X equals 0 is going to be the vertical asymptote because the graph gets closer and closer to it. We will spend more time on rational functions in a later section. So for extension questions, you may want to think about, if we know how the graph of 1 over x looks like, could we extend those ideas to 1 over x squared? And then if we know how the graph of 1 over x squared looks like, what would the graph of 1 over x to the power n look like, where n is a whole number? See what you can do.